Okay, simplify algebraic expressions. Yay! A whole lot of this will be, hopefully, very obvious, but we just want to knock it out just to make sure. So, unsurprisingly, we'll go through like terms first. 3 plus 5, I'm really hoping that we can do that. Brilliant, great, 8. Now, why are we doing that? 3 and 5, the only reason I've got this up here is to illustrate that these are like terms. They're things that naturally you go, yeah, I can put those together. Sometimes if you go all the way back to primary school, you'd be thinking, oh, I've got 1, 2, 3, and 1, 2, 3, 4, 5, and if I count them all up, eventually I get to 8. Fine, so you're considering this as 3 somethings and 5 somethings. Okay, fine. So when we go into algebraic thinking, I've got 4a plus 3a. If I think of these a's as, say, apples or anything, it doesn't really matter. Okay, I've got 4 things and another 3 things. Well, I'd have 7 of these things. Beautiful, easy stuff. Cool, I've got 8 bananas and I lose 5 bananas. Well, then I'd have 3 bananas left, so 3b. Nice and easy stuff. Cool, a plus a, well, if we use the words that we were saying, so it's an apple, I have an apple and another apple. Well, then I have 2 apples. If you're wondering where the ones came from, it's implied. The fact that there is an a already sitting there implies that there is 1a there. So I've got 1a and another 1a, so that gives me 2 a's. Beautiful. Alright, well, what if I've got b minus b? Well, I've got one of them minus another one of them. I've got nothing left, so I've got a big fat 0. Beautiful. Cool, what about this? Well, I've got these squares on there. Does that change anything? Well, actually, not really. I've got a squareds is this one object. I don't know what an apple squared is. It might be a squarish apple if you want, or a cubic apple or something, but we don't even care. It's just whatever these things are, there's 5 of them and another 3 of them. So I've got 8 of whatever these things are. Done. Cool. 4b squareds minus 1b squared. Well, whatever they are, I've got 3 of these things. Beautiful. Okay. Well, now this is looking a little bit chunky. I've got different things in here, but if I just rethink that, I've got a squared b's. So I've got this thing and this thing, 3 of them and another 2 of them. Cool, I have 5 of whatever these things are. That's it, that easy. Cool, well, I've got these things and these things, they match, so that's fine. I've got 5 minus 2 of them, so I've got 3 of whatever these things are. Cool. If we do a little bit of subtraction, 4 minus 7, well, that's going to be negative 3. If you're not happy with negatives, some of these things are going to go really badly, so we better make that abundantly clear. Cool, I've got 3 things minus 5 things. Well, now we start to break down a bit with our analogy of apples, because I have 3 apples and lose 5 apples, I have lost 2 apples overall. How does that really make sense? Well, we're going to say we have negative 2 apples anyway, because we can still think of that. How much sense that might make in intuition is another question, but we can still think in terms of that. I've got 2 things minus 3 things. Well, I've got negative 1 of those things, so I've got negative 1 of those things. If I put the 1 in there, that's okay, but it's a bit redundant because just having it there implies one of those things. Cool, 5 things minus 8 things, great, negative 3 of whatever these things happen to be. Beautiful. Cool, oh, well hang on, ABs and BAs, those are different things, aren't they? Well, if we go back and think about, hang on, what's 2 times 3? Well, that's 6. What's 3 times 2? The reverse order. That's also 6. So if we change the order of our multiplying, it doesn't matter. And that's all that these things are doing. It's just saying, I've got 2 times A times B plus 3 times B times A, so I could shuffle that order in my head and say, well, that's the same as 3AB. So I've got 2 ABs and 3 ABs, so that's just the same as 5 ABs. So if the order shuffles, still the same idea. Cool, what about this? Similar story, I've got a squared, b cubed. The b's are cubed, the a's are squared. Those match, so that's fine. I've got 9, a squared, b cubed. Beautiful. I go through this and say, oh, hang on, they all look a bit different, but I've got 1a, 1b, 1c, 1a, 1b, 1c, 1a, 1b, 1c. Yeah, they all match, that's fine. So I've got 2 plus 4 plus 7, gives me what, 13? And they're all just a, b, c. Now, I could, if I wanted to, change this to say, oh, that's 5ba, because these are the same, just a rotated order. I could make this, that's an equals, b cubed a squared. Critically though, this is not the same as 9 a cubed b squared, or 9 b squared a cubed. So the powers have to stay on the same letter. It has to be a squared and b's cubed. A squared b cubed, a squared b cubed, fine. A cubed b squared, no, wrong way around, similar story. So same with this, I could change this into any order of A, B, C that I want. I can change it into a new order that we didn't even see before. So C, B, A. That's a new order, it's fine. It's just a different ordering of it. But again, the powers have to move with those letters. Cool, or pronumerals I should call them. Cool, alright. A plus B, well, hang on, I've got apples and bananas. If I have an apple and a banana, what do I have? I've got an apple and a banana. Is there any better way of saying that? No, that's as concise as I can be. So this doesn't actually simplify at all. Doesn't go anywhere. I have A plus A squared. Oh, okay, well there's A's in there. Can I add these or do something to them? Is an A the same as an A squared? No, they're different concepts. So I can't actually do anything with this. Even though it looks really tempting, I can't actually do anything with it because they're talking about two different ideas. Cool. A B squared B. A squared, B squared, AB. Well, hang on, all of these are talking about different things. A with B squared is different to A squared with B, and that's different again to just A squared by itself, which is different again to B squared by itself, which is different again to A by B. So nothing in there has anything, there's no perfect matches anywhere in there, so I can't do anything with it. That's as simple as that one's going to get. Which is irritating, but at least we don't have to do any work with it. Cool, okay, going over. Multiplying and dividing now. Cool, so 2 times A, we don't bother to write the times in the middle. We always like to be as shorthand as possible, so 2A just means 2 times A. 3B means 3 times B, great. A times B, we just shorten to AB. Great, this thing, now, whenever you're running through, you just go through and try and find like terms, and then deal with that. So 2's and 3's are both perfect numbers, so 2 times 3, 6. A's, there's no other A's. B's, there's no other B's. So that's 6AB. This guy, okay, I've got pure numbers. Negative 3 by 4, that's negative 12. A by B, AB. A by A, okay, these are like terms again, so I can do something with them. Well, if I'm doing something times itself, we describe that as squared. So this is A squared. Now, this is only slightly shorter than that, but it ends up being a bit neater and easier, and it allows you to do a whole bunch of other tricks later. So, we've got this guy, okay, negative 10A divided by negative 5B. I find it's a lot easier to think about these divisions as fractions. So, we just go from top to bottom and try to cancel out anything that we can. A negative divided by a negative, well, that results in a positive. So, I'll write that in green just to say it's optional, just like we had, what was it? This. So that's an optional negative 1a squared, right? We don't actually need to write that one. We don't need to write the positive for this, but we can if we want. 10 divided by 5, that's 2. Okay, a divided by b. Well, they're not like terms, so I can't move those. So I've still got a on top, and then b is on the bottom. So I've got 2a over b. The plus you can put there if you want, but it's redundant. Cool. 2a over 3b, alright, so I've got 2a over 3b. Looking for like terms, 2 and 3 are like terms. 2 divided by 3, that's still 2/3, it's 2 on 3. I can't simplify this one any further, so he's stuck. A and B, they don't have anything in common, so they're stuck there as well. That one doesn't simplify. But it's usually a better idea to write it as a fraction like this than leave it as a long statement wherever you can. Just makes your calculations a lot neater and easier to see where things can happen. Cool, similar story, so we've got 2a cubed b to the 4 over 5a to the 6 b to the 7. Great, okay, do we have anything in common? 2 and 5, nothing's going to happen there, okay. A's and A's, B's and B's, so something can happen, okay, great. 2 over 5, nothing for that, so they stay. A to the 3, A to the 6. Well, I've got more on the bottom. How many more do I have on the bottom? I've got 3 extra A's on the bottom. remember that this is a times a times a on the top, and this is a times a times a times a times a times a on the bottom. So I can cancel off 3 a's from the top and the bottom, and then I'm still left over with 3 on the bottom. Cool. B to the 4, B to the 7. Well, I've got 3 more b's on the bottom, so 3b. Now, this looks a little bit wonky, so typically we'll move that 2 to the middle of the fraction, just so everything's nice and centered. You can leave it on the far left, it just looks really weird. And that's that. Next guy, same thing, write it as a fraction, make fractions your friend, because they make life easier. 10 and 6, well, I can't divide 10 by 6, but they both divide by 2. So what I can do is say, okay, this divided by 2 is 5, this divided by 2 is 3. Okay, A's, well, I've got 5 on top, 3 on the bottom, so I cancel off the 3 on the bottom, cancel off 3 off the top, I've got 2 left on top, so A squared. B to the 2, B to the 7, I've got 5 more on the bottom than I do on the top. Great. Cool, so that's simplifying. Now we want to do expanding. So expanding, all we're going to do is say the following. I'm going to have one loop, and then I'm going to have a second loop. So if we think about this, well, if we do BODMAS wise, 3 plus 4, 7, times 2, 14. So whatever result we should get should also be 14. Okay, first loop, and these loops multiply. So 2 by 3 is 6, and then 2 by 4 is 8. Keep in mind, we had a positive 2 times a positive 4, so that's a plus in between. 6 and 4 gives me 18. Now, that's all well and good, but we took a hell of a lot longer just to do the same thing. This is just so we have some basis for thinking about the rest. So what we're doing is these little loops to figure out how this thing goes. Because in this case, if I try to do BODMAS, x plus 2, they're not like terms. I can't do anything with that. So I need a new technique. We're going to use the loops. 3 by x, 3x. 3 by 2 is 6. It was a positive. So I get 3x plus 6. Those aren't like terms, so I'm done. That's as far as that goes. Great. Next one, 5 by 2x, that's 10x. 5 by 4 is 20, but that was a negative 4, so negative 20. Negative 3 by 2 is negative 6. Negative 3 by negative x, a negative times a negative, positive 3 by x, 3x. Cool. Now you might notice that, oh hang on, the x went on the end here, what happened there? If you want, you can shuffle the order so that you get 3x minus 6. That's totally fine. Notice that the sign sticks with whichever one it was assigned to. So if you've got a minus in front of something, it has to move with that thing. Yeah, so similarly we could have made this negative 20 plus 10x if we wanted. We could have had 6 plus 3x. Cool, that's a plus there because whenever there's no symbol, it's implied to be positive. Cool, this guy. Excuse me. Purple. Cool. We've got 3 things, doesn't matter, you just do a loop for each of them. And you get a pretty rainbow. 4 by x, 4x. 4 by y, 4y. And we'll do red because why not? 4 by negative z, so negative 4z. Same thing, so it doesn't matter, you could have 26 of these things, you're just going to have 26 loops, and then you just have a long list. Same idea. Cool, next bit, factoring, and this is called taking out a common factor, so I'm just putting common on the end there, because eventually we'll learn a lot more kinds of factoring. Cool, okay, so I want to find what's in common between these two. Well, 6 and 8, they both divide by 2, okay, so the thing that's in common comes out the front. Great. Okay, I divide each of these things by whatever was in common. So 6 divided by 2, 3, plus 8 divided by 2, 4. Brilliant. Well, if we notice, that should have been 14, right? 6 plus 8 is 14, okay. 3 plus 4, 7 times 2, 14, yeah, it still works out. Now that sounds very familiar. It's almost as though we just did the same thing backwards. And that's because expanding and factorizing are the same thing in reverse. So it's just like you have plus, you have minus, you have times, you have divide, you have expanding, and you have factorizing. Cool. Alright, so what's in common? 2x and 6. I've got 2's and 6. Now, hang on, the x, does that throw things out? No. We've got one term here and one term there. So you're only looking at the stuff that's separated by pluses and minuses. So 2x and 6, I could divide both of those by 2. 2x divided by 2, 2's will cancel, I get an x. Plus 6 divided by 2 gives me 3. 6x and 15, they don't, 15 doesn't divide by 6, but they do both divide by 3. So I can take a 3 out. 6 divided by 3 is 2. X divided by 3 isn't going to do anything. No, I should have said, sorry. 6x divided by 3, so the 6 and the 3 will interact to give me 2x. Minus 15 divided by 3 gives me negative 5. Done. Keep in mind, whenever you're not sure, whatever result you get, you can expand it and you should get back to where you started. So 2 by x is 2x, 2 by 3 is 6, 2x and 6. Yep. 3 by 2x should give me 6x. Yep. 3 by negative 5 gives me negative 15. Yep, all works out just fine. 10, 4, I can take out a 2. Gives me 5 minus 2x. Beautiful. Expand, check. Oh, now I've got 3 things. Well, what do I do here? Just like before, I did each thing in sequence. Here, I've just got to figure out what do they all divide by? Can they all agree on? Well, this has got x, this has got y, this has got z, so they don't have any letters in common. But the numbers, 12, 6 and 4, well, I could divide all those by 2. So take out a 2, 12x divided by 2, 6x. 6y divided by 2, 3y. 4z divided by 2, 2. Done. And as always, you can expand to check, so 2 by 6x, yep, that's 12x, sorry. 2 by 3y gives me 6y, 2 by, oh, whoops, I forgot a z, good thing. And checked. 2 by 2 times z is 4z. Cool. Next thing. Well, 3 and 4 don't have anything in common, so maybe I'm stuck. But this time I've got multiple x's floating around. Okay, so they agree on x's, great. 3x divided by x, just got the 3 left, plus 4x squared divided by x. So this has 2 x's on top, and I'm dividing by 1x on the bottom, so I've got 1x left over, and the 4 didn't change. Cool, and you can always check, x by 3 is 3x, x by 4x is 4x squared. Beautiful. Next guy. So we've got a whole bunch of stuff now. I highly recommend you just go through in order of perfect numbers and then go through alphabetical order. Back here, the alphabetical order changed, which was what was making it fiddly. Always, if you've got the option, write things in alphabetical order, and then you know which order things are going to come in. Cool. 5 and 10. Well, what do they have in common? 5. So you can take out a common factor of 5. Whoops. Cool. X's, yep, they're in common. Okay. Y's, they're in common as well. But hang on, I've got a whole bunch of y's in common. So you always take the lowest power. So in this case, x, the lowest power was a 1. Here, the lowest power is a 3. Cool, okay, so 5 divided by 5, well, that's 1. X squared divided by x, that's x. Y cubed divided by y cubed, that's 1. So x times 1, or 1 times x times 1. I don't need all the 1s, they're redundant. Minus 10 divided by 5, 2. X divided by x, 1, so it's redundant. Y to the power of 5 divided by y to the power of 3, so 5 on top, 3 on the bottom, so I'll end up with 2 on top. Beautiful. Cool. Next guy, what's in common? Well, I've got 12 and 15. I can divide both of those by 3. X's, I've got x to the 5, x to the 3. Always take the lowest power, x to the 3. Y to the 4, y to the 8. Y to the 4 is the lowest. Z to the 6, z to the 1. So take a z. Great. So I've got 12 divided by 12 divided by 3 is 4. X to the 5, x to the 3 gives me x to the 2. These two cancel each other perfectly, so it's times 1, but 1 is redundant. Z to the 6 and z, that's essentially a z to the 1, just the 1's redundant, so that's a z to the 5. Plus 15 divided by 3, 5. X cubed divided by x cubed is a 1, but that's redundant. Y to the 8 divided by y to the 4 is still y to the 4. Z divided by z is 1, so it's redundant. Great. The only time that dividing by and you get a 1 by itself that counts for anything is if everything happens, if all of this happened to be out the front, then you'd have a plus 1 at the end because you just have 1 times 1 times 1 times 1. But that's still 1. So you can't leave it blank. There still has to be at least a 1 in there. But most of the time you'll have something else. It'll be 1 times something else, in which case the 1 is redundant. Cool. So that's that. That's the very quick revision / intro if you have never seen it before. Hopefully you definitely have, and this is all just like, oh yeah, I remember this now. Cool. Best of luck to you.